This is part 2 of our discussion on tokenization, embedding, positional encoding, multi-head attention, and sublayers of an AI transformer in C++. This is the link to part 1. In part 1, we discuss various components of an AI transformer in C++. We discuss the tokenization process and its implementation, the embedding process, and we discussed a transformer architecture, the encoder and the decoder. Then we discuss each of these components, including the positional encoding, the multi-head attention, add and norm, feed-forward, linear, and softmax. So that's what we discussed last time. We discussed the implementation of each of these components. So this is the positional encoding implementation, the softmax, the linear, add and norm. Okay. Add means add a residual connection. Norm means layer normalization. Okay. And this is the implementation of it. Okay. And multi-head attention. So multi-head attention is based on scaled dot product attention. So we discussed this in detail and the implementations. And then the feed-forward network. So that's what we discussed last time. In part 2 here, we'll present a complete implementation of the encoder of an AI transformer in C++. That includes tokenization, input embedding, positional encoding, multi-head attention, add and norm, and feed-forward. Basically, this part of the transformer. We first implement some helper functions. So this is the header of the helper functions. We call it util.h. And this is the actual implementation, util.cpp. We type def a 2D doubles vector to be matrix D, okay, for convenience of programming. And the function f here is an activation function. Here it implements the value or well-defined linear unit, okay, which returns the maximum of 0 or the input argument C. And this softmax with one-dimensional input vector calculates the softmax of each of the elements of 1D vector, okay, and returns a vector that contains the softmax values of each of them. Okay. And this, okay, also called softmax, okay, it overrides this name, softmax, but the input is a two-dimensional matrix, okay, matrix D, and the max element is calculated from each row, okay, and from there we calculate softmax values of each element and return the softmax values as a 2D matrix. Okay. And add mat is simple. We just add two matrices and return the sum matrix. And transpose is to return the transpose of a matrix A. Map rule is to compute the product of two matrices A and B and return the product. Init matrix as input parameters n and m, which basically is a 2D matrix with n times m. And to begin, we start with 0 values and use this random number generator to generate some random numbers. And the standard deviation is the sigma is 0.2, and the mean is 0. So we use this 0 and 0.2, and so we generate the random numbers with these properties and return it in M. And print dictionary basically is to print the tokens, the dictionary that contains tokens in the form of an unordered wrapped of a string and int. So basically it prints out the first element, that's a string, and the second element, which is an integer. Print matrix is to print a matrix. The following are the classes implementing the components of an AI transformer. We discussed their implementations in the previous video. This is the classes header file, transformer.h. This is the tokenizer class. Words is an unordered map containing the token dictionary. The first element is the token string, and the second element is the index to the token, or the token ID. And the word index is the reverse. The first is the index, the second is the token string. N tokens is the number of tokens. So these are the member functions. And this is the embedding class. So again, n tokens is the number of words. Dim is the embedding dimension. M matrix is the embedding matrix. So its rank is n tokens times dim, or n tokens rows and dim columns. These are the member functions. The class Positional Encoding implements the positional encoding, this part. So max tokens is the maximum sequence length. D model is the embedding dimension, or basically the dim that we mentioned here. And the matrix PE is the positional encoding matrix. And these are the member functions. The class multi-head attention implements multi-head attention component. And the D model is the dimension, and N heads is the number of heads in the component. And DK is dimension per head. Basically, it is D model divided by n heads. And the matrices WQ, WK, WV, WO are weight matrices for Q-ray, key, value, and output. Okay, these are the member functions. And this is the transformer encoder that implements this part, okay, the encoder. So there's primary members, D model, dimension of the whole model, n head, number of heads, dk, dimension of each head that we mentioned here. N tokens is the number of tokens, and multi-head attention, MHA, this will be a pointer pointing to a multi-head object. This part. So this is the actual implementation. Then let's go through these classes briefly. This is the tokenizer class, the default constructor. It could create a simple dictionary from a simple sample of words, okay, like this. And this is another constructor with input parameter IF stream. So we obtain the data from an input file stream and pass them into tokens. Okay. And get token words is to return the dictionary, return words. And tokenize a string, I would take the input string and pass them into the corresponding token IDs, okay, and return all the IDs as a vector. And detokenize is the reverse. We change a vector of token IDs, okay, back to the text. Okay. It is first we look up the word string of the token index, okay, and then combine them with a delimiter. Then we return the string. Get n tokens returns the number of tokens. Now this is the embedding class, and this is the constructor. N tokens will be the sequence length we pass in, and dim will be the embedding dimension we pass in as input parameter. And the constructor will initialize the embeddings as an n tokens times dim matrix with certain random values. We use this helper function we discussed earlier, init matrix, to do the initialization. So the values are returned in this matrix. And this we create the embedding matrix with the token IDs. We pass in a vector of token IDs and then create embedding matrix and return the embedding matrix. So get embedding returns the dimension of the embedding matrix. Get n tokens returns the number of tokens, n tokens. This is the positional encoding class. This is constructor with maximum sequence length and embed dimension. So basically, maximum tokens is the maximum sequence length, and D model is the embed dimension. And we applied the formulas we discussed last time to create a positional encoding matrix. Okay. And this is to add the positional encodings to embeddings. We use this function add PE. That's very simple. We just add this the positional encoding to the embeddings we pass in, and then return the sum. And get PEs is to return the positional encoding matrix. And this is the multi-head attention class. The constructor initializes the D model n heads with input parameters dm and nh and calculates the dk. And it calls init matrix to initialize the weight matrices WQ, WK, WV, WO. And the compute attention member function will compute the attention, like this figure. Say the input is the embedding matrix X. So the dimension of X is n tokens times D model. And it first calls a mat wheel to obtain QKV from WQ, WK, WV. So the mat wheel matrix multiplication is basically the linear operation here. And then it calculates the self-attention of each of the subhead, the scale dot product attention. And after that, it concatenates all the attentions from each head, as we discussed last time. So this is kind of after that, it goes through the linear this part to obtain the final output, and it returns the output matrix like this. Now this is the transformer encoder class, and this is the transformer encoder constructor with input parameters embedding dim, the embedding matrix dimension, and number of heads, and the feed-forward level dimension. So again, that's the initialization, and it creates a multi-head attention object using the model n heads obtained here. And so this MHA pointer will point to this object. And MHA attention will call the compute attention, the member function of the multi-head attention class, to calculate the attention. And this is the norm function, which is straightforward. And this is the feed-forward network. And we discussed this last time. And this program tests encoder .cpp is a main program for testing the transformer classes we just discussed. So we create the tokens using a test file t.txt. So we open this file and pass in the file stream to the constructor tokenizer. And using the member function get token words, we obtain a dictionary that contains the tokens, and so we print this out. The get here is to give a pause so that we can examine what have been printed out. And we also use a sentence. This sentence, the wave crash force rate against the shore, this sentence, and we tokenize it, and we print out what it looks like, what the token looks like, and give a pause. Then we create embeddings. We set the model to be 8, and the total tokens will be given by the tokenizer, get and tokens. So we print out the total tokens and also the model. And we create an embedding object. We call it embedding layer with the parameters, total tokens, and the model. And the member function of this embedding object, we return the embedding matrix. So we call this embeddings. And so we print out the dimension of this matrix and use the utility function print matrix to print out the embeddings matrix. And give a pause, click here. Then we create positional encodings. We set the maximum sequence length to be 16. The D model is 8. So we create a positional encodings matrix using get PE. So we put it in PE. And we add the positional encodings to the embeddings using the member function add PE. So we add the positional encodings to the embeddings. Then we first print out the positional encodings only. There's a matrix PE that we get here, print matrix. And then we have added this to the embeddings, so we print it out again. That means the positional encodings with embeddings. So this part, so basically we add this to the positional encodings, and this will fit to the multi-head attention. So this we pass through a transformer encoder, and first we get the dimension, the embedding dimension from this member function, and we set the feed forward network dimension to be 128, and create a transformer object. Transformer encoder object, we call transformer encoder, using this dimension, and 8 and DFF 128. Then we print out the information. So we use this member function MH attention with these input parameters, embeddings with positional encodings as inputs. So this will calculate or compute the multi-head attention, okay, and we get the matrix we call it Y, and actually this will be after linear, so we print this out. So that means we print out this part here. Okay. Then after this we add a norm, and then go to a feed forward and add a norm. So we print this out, okay. Add and norm. We call this function to do the add and norm. So we print and return to matrix. We call it Y1. So we print this out again. Okay, there's multi-head attention after add and norm. Okay. And we feed this to the feed-forward network. Okay. So we need to create two matrices, W1, W2. Okay. And again call init matrix to initialize the weight matrices, and call the member function feed forward to do the work, and it returns the output as Y2. Okay. Again we print out this, okay. So now it is after feed forward, and finally it will go into add and norm. So we again print out the data after add and norm. Okay, so that's what this diagram shows. Feed forward and then add and norm. Okay. And we also try to tokenize the token to to reclaim the original sentence. Okay. And this is the makefile for compiling the programs. Now let's copy these programs and compile and run it and see how it works. So we just highlight this and copy it. So for example, transformer.h. So we just copy this, okay, and then paste it into a file. We've copied all the files to this directory. This is the util.h, .cpp, and the transformer classes header, the .cpp file, and the testing program, the makefile. Okay. And this is the t.txt, the testing program. The testing test. Okay. These are extracts from the fiction, the Ping Pong Hustles. And now we can create an executable by typing make. So it compiles the programs to test encoder. Okay. So this is the executable. So now let's execute test encoder. So the first it prints out the tokens. Okay, tokenization. So these are token IDs, and we tokenize one sentence. This is the sentence we considered. Okay, and the corresponding tokens, okay, are these values. Okay, so there, okay, is 36. Okay, so this is there. Okay, for example. Okay, and then it prints out the vocabulary size. So the total is 77. So there are 77 tokens in the dictionary, and we make the embedding dimension to be 8. Okay, so this will be the token embeddings 8 times 8. So it is created using this init matrix, okay, with a standard deviation or sigma to be 0.2, and the mean is 0.0. So you can see that these are random values, okay, for the tokens with dimension 8. And then next, okay, is the positional encodings. So the dimension is 8, so it prints out the positional encodings for 16 tokens. And this is the embeddings with positional encoding. Basically, we have these positional encodings added to the token embeddings. That is negative 0.082 added to 0.0, we get here negative 0.08. And this one, okay, 1 plus minus 0.23, so we get 0.72, and so on. Okay. And then next, okay, the data passes through the transformer encoder layer, and this is the multi-head attention output after linear. So you get this output from the multi-head attention component. And then this will fit into add and norm. Okay, so we get these values. Okay. So after this add and norm. And then this, okay, is feed forward data after add and norm. Okay. Okay, that means at this part. Okay. So we get these values, and then these are the data for the tokenization we obtained in the original sentence. Okay. So this is a simple transformer encoder. So you can also copy the files from the website, okay, and compile them and try them yourself. And of course, you can also modify the programs and play with them. Okay. So this wraps up our discussion on this topic. Okay. Thank you for watching, and I'll see you in the next video.